Hello everyone. So this is part B for lecture 8 part B. So today we're gonna do the predicates, and we already know what's a predicate and what the difference between predicate and propositional logic from the introduction lecture. Okay, that was in the first week. But let's build on that and go deeply a little bit and consider what is a predicate. So, okay, predicate. Before we go and explain what's a predicate, let's revise what's a proposition. So a proposition are absolute, which mean that the value for any proposition is either true or false, cannot be both, cannot be undetermined. It should be either true or false. So the proposition has an absolute truth value. It could be either true or false, and also does not depend on circumstances. Its value, it's known and doesn't depend on other parameters. يا شباب, okay? And as I said, values are either true or false, and the propositional logic is not powerful enough to model a real world situation. That's why there is something called predicate logic. So predicate logic, it's more general than propositional logic because predicate logic is a proposition, by the way, but it depends on variables. So like, for example, I'm gonna use this notation to denote that X is green. So there is a function called g of X to calculate whether X is green or not. So what's X? It could be anything that has a color, ya shabab, okay? And if the color for X is green, g of X would be calculated to true. And if X has different colors than green, it would be calculated to false, ya shabab, okay? So, like for example, now I'm gonna say G of grass. Grass is a thing that has a color of green, which means that G of grass, its value is true. However, I'm gonna say G of tomato. So the tomato thing, it has a color which is not green, which is red, which means that when you calculate it, its value is false, ya shabab, okay? So now we assume that you have a predicate logic to model something. In order to convert it to propositional logic, you need to substitute, you need to do an instantiation to substitute with a value instead of X, and this value should belong to something called the universe or the domain for the variable X. Okay, shabab? So let's continue. So in order to transform from or to convert from predicates to propositions, as I said, we need to do something called instantiation. So the truth value of a predicate depends on the value of the variable itself. So when you substitute, you check whether the substituted value satisfies what you want to check or not. If it satisfies it, so its value is true. If it's not, so its value is false. And this variable should be drawn from some domain which is known. Okay, shabab? So now how to go from predicate to proposition? It's very easy. So if the proposition is called P of X, which denotes that X is, okay, so what's P of X? So I'm gonna say that P of X represents that X is one of the set of people. And now I'm gonna say, okay, I will substitute with A, with X equal A, which means that I will convert P of X from having a variable X into P of A, and now I can check whether P of A is calculated to either true or false. Okay, so like for example, again, G of X, the example I just mentioned in the previous slide, it means that X is green. So G of blood, the blood color is not green, it's red. So which means that if you instantiate X with blood, so the overall value for the predicate logic, it's converted now to a proposition which has a value as false. However, G of grass, now the grass has a green color, its value is true. So in the propositional logic, we're gonna use quantifiers. This is called for all, and this is called there exists. Okay, Shabab? So what does this mean? How can we read it, ya Shabab? I'm gonna say for all values of X, P of X is true, okay? And of course, I mean that for all values of X inside a certain domain, ya shabab. If the domain is not shown in the modeling, it means that you have only one domain, okay? You don't have to write it. And this one, there exists X, a value, at least one value from the domain in which P of X now is true. Okay, shabab, this is how we read it. So this sample, it means for all values, and the condition should hold over all the elements inside the domain, while this one, there exists at least one value, at least satisfies the condition P of X, okay? Okay, great. So, why do we need domains? Why do we need to define a domain? Because, like, for example, if, okay, I'll explain this slide, and after that, there is another reason behind domains. If you have multiple domains, so you need to identify which domain you consider currently in your statement. But as you know, why do we need domain? The predicate G of X must be either true or false after instantiation. So when you substitute a value for X, you need to be able to calculate the overall truth value to be either true or false. So we don't have other possibility. We have either a value of true or a value of false, which means, ya shabab, if you have G of X being calculated to be true, its negation, not G of X, will be calculated to false. And if you do exclusive OR between the two expressions, the propositional logic or the predicate logic, when you do instantiation and its negation, the overall value should be true يا شباب. So XOR between true and false, it gives a value of true. So, and this is a condition for any propositional logic. Anything to be a propositional logic, how we make sure that this is a propositional logic. So you go and check this condition, find its true value, find its negative value, do exclusive OR between the two values, the result must be true. So let's consider the previous example, g of x, where g of x, it means that x is green. Now, g of grass, and grass is green, it's being calculated to be true. G of blood, and blood is not green, it will be calculated to be false. So it was very easy and it was correct because grass has a color and blood has a color. What about if we substitute for x with a value equal to love? What g of love? So g of x, it means that is x green? If it's yes, its value would be true. If it's no, its value would be false. So if you answer with yes, it would be true. If you answer with no, it will be false. So now, what's g of love? So the first intuition would be like, okay, is love has a green color? It would be no, it's not. Love is not green, which means that its value is false. Okay, so you just calculated g of love to be false. So let's continue the next slide, and I will show you that the importance of defining domains. Now, let's define another predicate, which is NG, stands for not green. NG of x, so I will ask that, is x not green? If you answer with yes, so it would be true. If you answer with no, it would be false. And again, because we know that NG of x is the opposite of g of x. We know that, okay? So let's apply g of love, and we said that its value is false. Let's apply ng of love and check whether ng of love is true or false. So is love has a non-green color? Of course, no, which means that the value would be also false. So now, and why it's false? Because actually love has no color, okay? Which means that the statement is false. So now, ya shabab, we said that in order to be a propositional logic, the XOR between g of x and negation of g of x should be true. So now g of love, it's false, and not g, which is ng, of x, and you substitute with x is equal to love, is also false. So now the exclusive OR between false and false, it gives false. So how come this is a predicate logic or a propositional logic? It's not. No, it is a propositional logic. It was a predicate logic before substitution, but you need to carefully define what is your domain. Because love, ya shabab, has no color, you cannot include love as being a member of the domain that's applicable for the predicate logic you do, you design, okay? So you just say g of x, where x has a color. So now love cannot be inside this domain because it has no color, ya shabab, okay? So this is the importance of defining domains. And also here, what if your statement contains more than one domain? So you need to specify now which domain you're dealing with. So, okay, let's understand what does for all and there exists the universal quantifier and the existential quantifier mean. So suppose that a domain D consists of 3 students and D contains 3 student names, Joe, Anne, and Bob. And now I'm gonna model a statement P of X to mean that, or to model that X has a pen. So if X, who is one of the domain, had a pen, it would be calculated to true. If X has no pens, so it would be calculated to false. What does this statement mean? For all X inside the domain P of X, it means that for all X, it means for every instant inside for every instant inside the domain Joe, P of Joe, Joy, and P of Anne, and P of Bob. This is when you calculate it, it gives a true value because this means that it is true for all instances X inside the domain. So it means that Joe already has a pen and has a pen and Bob has a pen. Okay, so the universal quantifier, it means that it's true for all instances inside the domain, while for the existential quantifier, it means at least one of them has a pen. So Joe has a pen, or Anne has a pen, or Hope has a pen. Okay, so this is the difference between for all and there exists X where P of X is true. Okay, shabab. So universal quantifier, it's and between all the instantiations, and existential quantifier, it's or between all the instantiations, shabab. Okay, great. So what if you have multiple variables? As I said, predicates may have more than one variable to model and maybe more than one quantifier to use. So like, for example, what does this mean? And be careful, ya shabab, this is very important to understand. So you may expect something like that in the exam. So would it be calculated to true or false? What is the truth value for this propositional? This is predicate logic. How we read it first? So let's try to read it. I'm gonna say for all X, and by the way, X and Y belong to the set of integers, okay? So for all X, where X is an integer, so for all integers, there exists Y where Y is an integer. So for all integers, there exists a value Y where X plus Y satisfies this equation, X plus Y equals 0. Is it true or false? So for all X, if X is 1, if X is 2, if X is 3, and so on, there exists a value Y. So I'm gonna check for all values of integers whether there exists a value Y that satisfies the condition or not. So now the condition is that X plus Y is 0, which means that the value of Y that satisfies this condition is that y equal minus x. So now if x is 1, y is minus 1. If x is 2, y is minus 2. If x is 3, y is minus 3. So like for example, if x is a, y is minus a, where a is an integer and minus a is still an integer, which means that this predicate logic is always being calculated to true. Okay, Shabab? So what if I will convert this a little bit and write for all x, for all y, x plus y is 0. How we read it? For all integers x, for each integer x, all values of y satisfy x plus y equals 0, which is not true. Because if x is 5, for example, and y is 2, x is 5 and y is 2 does not, these two values do not satisfy the condition, which is x plus y is 0. So changing a quantifier, it changes the overall meaning and it changes the model itself. So be careful, Shabab, when you read it. Okay, great. Negation. Can we negate a quantifier? Yes. How we read it? It's like, okay, here for all values of x. Here, not all x. So not all x satisfy p of x, which means English-wise, if not all values of x satisfy p of x, at least there exists at least one value that does not satisfy p of x, does not satisfy p of x, where p of x is false. So ya shabab, this is exactly has the same meaning as there exists x, where p of x is false. So I'm gonna negate p of x, because p of x, it means that this is true. If p of x is false, it means it could be modeled as not p of x. And in order to prove this, it's very easy. So do you remember, ya shabab, what was the value of for all x p of x? It means that p of x1 and p of x2, and until you reach the last x, p of xn, for example, it's being calculated to be true. Yes, this is the for all. So the negation, it means that you're gonna negate all of this. And using De Morgan's law, you will distribute the negation inside the bracket. So it will be not p of x1, not p of x2, until not p of xn. And actually, the conjunction, it would be this junction. And d, it would be converted to or, and so on. And you know that or, it's the model for there exist. So there exist, and here is the predicate. There exists a value of x where not p of x is true. So this is exactly the same as this one. So we say it, ya shabab, the negation negate for all x p of x. De Morgan's law, it means that there is another form which is exactly equivalent to this part. So the negation can move to inside, but while moving to inside, the quantifier would be flipped, would be changed from being for all to be there exist. So there exists x where not p of x. So يا شباب بالعربي النيجيشن ده بره، علشان يعدي الكوانتيفاير هيقلب الكوانتيفاير من انه for all يبقى for there exist. And same, and this is the next slide actually, if there is not before there exists x where p of x is true, it's equivalent to النيجيشن دي عايزه ادخلها جوه، اقول له خلاص when you move the negation the quantifier is being changed from being there exists to be a universal quantifier, so it would be changed to for all x والنيجيشن دخلت جوه not p of x is true. اوكي سو الليفت سايد والرايت سايد هنا زي بعض عشان ده بدي مورجان لو وده البروف بتاعه. اوكي so how we read the negation before the existential quantifier, this means that there exists x where p of x is true. So if there is a negation before it, it would be read as there exists no value of x where p of x is true. So English-wise, we can rewrite it as there exists no x, which means that for all x, p of x cannot be true, so I'm gonna negate p of x. So actually, this is exactly the same equivalent to the other form. And in order to prove it, it's very easy. So there exists, do you remember how we model there exist as a function of propositional logic? Yeah, it's being or between all the instantiation. And the negation before there exist, it means that you're gonna apply the negation over all the values inside the bracket. So this would be negated, this would be negated, this would be negated as here, but the OR operation would be converted to be AND operations. And you know that the AND between all the instantiation, it's being the equivalent form for the universal quantifier for all x. And actually, this is a new predicate now, not p of x is true. So this is exactly the same as the given negation for the existential quantifier. Okay, so rule يا شباب ان النيجيشن يعدي الكوانتيفاير مفيش مشكله، بس بيقلب الكوانتيفاير هنا، يقلبه from being for all to be there exist, from being there exist to be for all، والنيجيشن يعدي لجوه. اوكي حلو جدا. So scoping rules. What if I have this situation? There is a student in the room and a question to be asked. And now I'm gonna model this situation as two parts. I have a predicate called S of X. It means that X is a student in a room. And A of X, it means that X is a question to be asked. And now it's being linked by AND, so I will connect the two by AND, and that's it. So the definition, the modeling is not totally correct because now you're gonna be confused between the X on the left side and the X of the right side. So now you need to specify if you're gonna say there exists X where S of X and there exists X where A of X, so it's not that true because this X is different than the other X. And actually, the first X belongs to the domain of people or students, and the other X belongs to the domain of questions. So now we need to define domains by saying that P will model the set of people while Q will model the set of questions. So now we have two domains, okay? And now I will say that, okay, the modeling would be a little bit different because I'm gonna say that, okay, there exists X from the domain P where this X is a student. and there exists X from this set of questions where this question will be asked. So it means that this X belongs to the domain of people, where the other X belongs to the domain of the questions, which is now modeling the correct situation. So if you have more than one domain in Shabab, you need to explicitly specify the domain. And in order to specify the domain, we need to use the colons between the variable and the domain, ya Shabab. Okay, great. So predicates and conditions, implication. So let's consider this statement. If one drives a car, then one can get to the station. لو حد بيعرف يسوق عربية هيقدر يروح المحطة. So this is the condition and this is the goal, the consequence. So we can model this as f for all x belongs to the set of people P. And now X here refer to one of the people and here refer to one of the people, which means that you have only one domain, so you don't have to write it clear explicitly like this. But if you already want to write the domain, it's correct. Okay. So for all X from the set of people, if this X can drive a car, then X can reach to the station. So I'm going to use two predicates, D of X, which means that X drives the car, and R of X, which means that X can reach to the station. Okay, Shabab? Okay, and let's consider the meaning. So if you have the Venn diagram here, those elements belong to the set of people who can drive a car. Those elements, including D, of course, represent the set of people who can reach to the station. So you can reach to the station by either driving a car or using any other way of transportation. You can walk to the station, you can have a bus, you can using any different way, you can do cycling to the station. And the others are the set of people who are not driving and also cannot reach to the station. Okay, so R is the set of people who can reach the station. D is the set of people who drive. And now the implication, it means here, if X is not driving and cannot reach to the station, so I mean one like this one. Here X cannot drive and also cannot reach to the station. It is correct. If X cannot drive, okay, but like here, it can this X can reach the station, so it is correct. He or she can use any different way of transportation to reach to the station. But if you mean like this X can drive, and of course X inside the set of R, which means that R of X is also true, which means that X can reach to the station. So this is true. But can we have an X where this X can drive, so it's one of this set, and at the same time this X cannot go to the station? No. So now I'm referring to one inside and one outside, and it should be the same one, and it's not possible, which means that the statement is false. Okay, Shabab? So now this is for all X if X can drive, then X can reach the station. So now let's consider the sufficient and necessary condition. We already studied this before when we were dealing with the propositional logic. And now for predicate logic is the same way. If I'm saying that for all values of X, if D of X is true, this implies that R of X is also true. So the sufficient condition, it means that D of X being true, it's sufficient to have also R of X being true. Yes. But if D of X is false, it has no meaning for me. Okay, if X cannot drive, do I have a confirmation that X cannot reach to the station? No, I don't have, because like X can use a bike in order to go to the station. X can walk to the station. X can use public transportation to go to the station. So the sufficient condition, it means that it has a positive way of dealing with the implication. So having the left side being true, it's sufficient enough to say that the right side is true. So what about the necessary condition? So R of X is necessary for D of X, and it should be dealt in a negative way. So if R of X is true, it means that X can reach to the station. Does it mean that X know how to drive? Is not necessarily. But if I'm saying that X cannot reach to the station, so 100% X cannot drive. That's why I meant that the necessary condition, it's being dealt with the conditional statement from the right side to the left side in a negative way. So having the consequence, the goal being false, is fair enough, is necessary to have also D of X being false. Okay. Okay. So necessary condition have negative meaning, and sufficient condition has positive meaning. Sufficient condition has positive meaning in the same way. A necessary condition has negative meaning in the opposite way. Okay. Okay. So the strength of conditions. So assume that we have this Venn diagram. So we have set F, which means that anyone inside set F can drive a Ferrari. And set D, which is a superset of set F, anything inside set D, it means that he or she can drive a car. And R, it means that it can reach to the station, and M, it means that it can move around the town, and A, it means that is alive, and the universal set is a set of people, it's a person. So I can say that, okay, for all x's, if it's f of x, if f of x is true, now if x can drive a Ferrari, so X can drive a car. Yeah, because Ferrari is a car in general. And if X can drive a car, it means that X can reach to the station. And if X can reach to the station, it means that X can move around. And if X can move around, it means that X is alive. حاجة حية. So يا شباب دلوقتي احنا عندنا شرط أول يحقق نتيجة، والنتيجة دي شرط الحاجة اللي بعدها. And this is a condition to another goal, and this is a condition to a last goal. So Now we can name the first condition to be something called a strong condition. And the last goal is named as a weak condition. Okay, Shabab? So, and using the rule of syllogism from rules of inference, if A implies B and B implies C, we can conclude that A implies C, يا شباب. Okay? So, why are conditions useful? Because, like, for example, let's deal with this situation. We'd like to know whether a string is a palindrome or not. A palindrome, it means that this string, the same way you read it from left to right, is exactly the same pronunciation when you read it from right to left. So like 2, 2, when you read it from left to right, it's the same when you read it from right to left. 3, 5, 3, the same pronunciation from left to right is the same pronunciation from right to left. So I'll try to put a condition in order to say that, okay, this is a palindrome. And the condition is that the sufficient condition, if you find it, it's fair enough to say that, okay, this is a palindrome. A sufficient condition could be that the string is a sequence of identical characters. So if you have only one appearance of characters of the same character again and again, like A, this is a palindrome. So having identical characters, it's sufficient enough to say that this is a palindrome. And the necessary condition, there are repeated characters. And now let's here, like for example, 3 and 5 are repeated characters. E and E are repeated characters, and so on. So let's assume that we have a string of 100 characters. How do you go about testing whether it's a palindrome or not? Using conditions. Okay, so let's prove it. If you find that this is repeated character, it's a string of one character being repeated, so this is from sufficient condition, so it's a palindrome. So if you have repeated characters, is it enough to judge that this string is a palindrome? It's not enough, ya shabab. Like for example, A, B, C, A, A. Now we have repeated character, okay, which is A. But the same way the way you read it from left to right is not the same as you read from right to left. So that's why you need to differentiate between the sufficient condition and the necessary condition. Yeah, shabab. Okay. Okay, great. So the last slide here, what if I'm saying that this condition is necessary and sufficient for something? So like, for example, a number is divisible by 3 if and only if the sum of its digits is divisible by 3. So I'll say that, okay, a number being divisible by 3, it's sufficient to show that the sum of its digits is divisible by 3. And I'll also say that if the sum of the digits of a number is not divisible by 3, it means that it's necessary to have the number which is not divisible by 3. So if the modeling could be used as necessary and sufficient at the same time, it means that this is the modeling for f and only f. So for all x, if c of x, then g of x. And if it's g of x, it's also C of X. So this is a bidirectional implication, okay? It means that the C and G are identical sets, okay? So this is the end of the lecture. Thank you and good luck.